characters have been destroyed by previous lectures, but now, now things are going to be comfortable and easy. It's big room, but it would be 80 minutes. So these are 80-minute slots, right? This is a long slot, so it's tempted to go into autopilot and start reading your email. But what would be more fun for me is if you would sort of interact a bit, ask questions, make comments and observations. I don't know you all, so some of you will know some stuff, some of you won't know so much stuff. Please don't feel that your question is too stupid to ask, right? If you have a question in your mind, you're not following something, chances are there's at least another half dozen people in the room who are just wishing that somebody would ask that question. So please go right ahead and do that. And we will finish on time nevertheless. So I want to give you just start off by giving you a little insight into the life which you have now introduced yourself. That is the life of a programming language researcher. So of course what programming language researchers do is they invent programming languages. And here is the typical life cycle of a programming language. Right, so this is you, right? That's just you, the only user, that's right, the author and user, and a year and you're ready for a new language, right? So this is... So, of course, not all projects go like this. Some are successful. Here is what successful research projects look like. They kind of die more slowly after reaching 100 users or so, right? And of course, some languages, like C and C++ and Java and so forth, hit that threshold, cross the threshold of immortality, above which they can no longer be allowed to die because there's so much code written in them. For better or worse, C++ and Java and Ruby and so forth are with us essentially forever. I nearly put the regrettable absence of death, but I thought that would be rude, so I didn't. But complete absence is definitely the case. This is what Haskell could have been like, right? So Haskell was designed by a committee. This is the typical life cycle of committee languages, right? They never have any users at all, right? But Haskell, curiously, was designed by a group of academics starting about 1986 or so. So it really is a committee language, but it's one that did not follow the committee language life cycle. Here's Haskell's life cycle. So starting back in 1990, we've sort of done this kind of stuff. Then there was a fairly long plateau, which we were sort of sitting as a university-like language. And then just in the last 5 or 10 years, there's been a very noticeable uptick in interest in Haskell, which is strange because it's considerably older than Java, right? Java appeared for the very first time back. I mean, you're too young to know, right? But Java appeared back here, right? Haskell predates Java by a long time. And yet, I feel as if, we're only just getting going, right? Let's see. One other way to look at it is this is barely legible. I like this site, because it's one of these completely unscientific language popularity websites. But they're fun to look at every now and again. And I thought I'd show you this one. This is Langpop. I updated it a few minutes ago. So this is obtained by mining data on source code repositories and see how much programming languages are used. So, there's C and Java and C++ and PHP. And hey, here's Haskell, right? So you can see where it is. And hey, we're on the scale, right? For an academic language, this is just amazing, right? Usually kind of somewhere down here. And where are we with Scheme and Delphi and Lisp and ActionScript? I mean, you all know ActionScript, don't you? That really popular language. So we're down here. So this is how much languages are used. But what's very curious about Haskell is that this same site, one of the reasons I like it, also mines Stack Overflow and Reddit and all that sort of stuff to see what people are talking about, right? So if you look at the languages people are talking about, Haskell is, number 5 in the world. Don't you think that's amazing? Right, we're right up here, right? Way above JavaScript, PHP. Well, that's just down here somewhere. So to a first approximation, Haskell appears to be a language that everybody talks about and nobody uses. But my aim in these lectures is to reverse that trend, right? At least you can be the shock troops of Haskell taking it into the 21st century. Why is Haskell talked about a lot, but not used very much? Well, we can leave the not used very much, but the talked about a lot, I think, is because it's a sort of laboratory for interesting ideas. So it's as it's purely functional, right? So there's immutable values of the default, and we've thought quite a lot about controlling effects. So you'll have all heard of monads, probably. It's a lazy language, and we'll see some examples of that and why that's useful in these lectures. It's very good on concurrency and parallelism, by which I mean making things work in parallel because you're doing parallel I/O, but also just parallelism to gain performance. Good for domain-specific embedded languages, but for the purposes of this week, it's a crazy laboratory for type systems. Any kind of weird stuff you want to do in type systems, Haskell is your home. But it's a home that we try to make, we try to embody crazy type systems ideas in a way that they're still usable by ordinary programmers. Well, at least some extraordinary programmers like the people in this room. So you'll have to be the judge of that towards the end of this week. But this is, I think, what I'm hoping to do is not so much interest you in the language itself per se, but give you a little bit of practical insight into the way some of the type theory ideas you've been studying this week may show up in programming languages. Okay? That's the plan. So today, today this is kind of extra lecture. I wasn't actually going to say very much about type classes, because I expect some of you come across them, but since we had a gap in the program, I thought I would tell you a bit about Haskell's type classes and also how they relate to object-oriented classes. So that's hence the title of the talk. What are these class things that live in the object-oriented world and the Haskell world, and how do they fit together? That's the plan. Okay? That's today. So, just think, I don't want to assume that all of you are already experts in Haskell. So I'm going to just spend one slide going through sort of basic syntax of Haskell. And please then, at every stage after, I'm going to put up lots of typewriter font. If ever you see a phrase or something on the screen that you don't understand, ask a question, right? Because I'm not mind reader. I can't figure out what you don't know about. And if you stumble on syntax, then everything else becomes difficult. All right? Is that it? Promise? Wave if you agree. Wave. That's good. Okay, you're awake. Excellent. Thank you. Okay, so this is the filter function in Haskell. So it takes a function from A to bool, and so square brackets, that means list of A, and it's just defined by pattern matching. So P is this function, and in Haskell square brackets, this means empty list, and this is colon means cons, so that's the list construction operator. So if we filter out, we want to keep all the elements of the list that satisfy this predicate. So if the list is empty, the result is empty. Otherwise, if the list has X as its head element, and this vertical bar says if P of X, P applied to X is true, then return, I want to cons X onto the result of filtering the rest of the list. Otherwise, I just filter the rest of the list. So these vertical bars are guards, they're just Boolean valued expressions. Let's see, it's polymorphic, functions as first-class values, and the bit at the top is just a type signature, which typically in Haskell is written separately. So far, so good? Anything strange? Okay. Just one thing to watch out for, of course, I think most of you will have seen this before. Function application in Haskell is so important that it's written in the quietest notation of all, namely white space. So this means filter applied to P and X's, so we do that rather than writing it in a more conventional uncoded way at the bottom. Okay? Now, so that's okay for ordinary functional programming. Beg your pardon, sorry, just the data types. So we're going to see a lot of algebraic data types declared just as in ML. So here's Booleans. So Booleans are not built in. They're just a data type declared in a library, as are lists declared just like this. So this says Boolean is a type with true and false as constructors. All right? Now, let's talk about types. So now we get to an issue that we stumbled on when we were first designing Haskell. The idea was to try to embody much of the conventional wisdom about how functional languages should be designed. This was in the late 80s. But there was a stumbling block with functions that were almost polymorphic, but not quite. So member is a good example. It takes a value and a list of values of the same type and returns true if the first argument is a member of the second. Okay. Now, this looks as if this would be a sensible type for such a function, but it's hard to make it work for any type. Right? And the types that it's hard to make it work for, things like functions, right? So is negate a member of this list? So in Haskell, literal list is just written with square brackets. So this is a 3-element list whose members are negate itself, the increment function, and this function lambda x, so backslash is lambda x, 0 minus x. So this, of course, is negation as well. So you see the problem, right? How do we compare functions? Oh, we don't have equality on functions, so maybe this should be rejected somehow. See the problem? And this occurs all over the place, right? So if you want to sort something, you need to compare values for equality. If you want to add them, you would like add to work on all numeric types. If you want to serialize them into a bit string, you would like that to work on all types, but probably not on functions. You see the problem, right? So, and a variety, when we were first designing Haskell, there's a variety of kind of ad hoc solutions to this. So the ML solution is what I've called here local choice, meaning you can write plus in your code, but you always mean plus on floats or plus on ints, right? So if you were to write in your, I've got to erase the existential types. It would be good if we had an eraser, yes. If you, in ML, if you are going to write x equals x plus x, then this is kind of rejected because we don't know which plus you mean. So you're going to have to somehow say, oh, this x is a float. But then if you want to work on doubles, you have to write another function. Does that make sense? So it's kind of, it's local choice in the sense that you can use the same symbol, but it always means, it's really shorthand for a particular one. Does that make sense? Okay, so that's one thing you can do. Another thing you can do is what object-oriented languages typically do, which is to build into the very fabric of the runtime, you build in some of these quasi-polymorphic functions like equality or hashing or serialization. So every object supports these, right? And so this is fine for a fixed vocabulary of built-in functions, but it's really not very good for if you want to make this extensible. And also, you can get runtime errors if you try to serialize something that isn't serializable. Okay? You with me so far? Yeah, that was a thumbs up. Good, not a question. Ah, right. Exothermic activity, need more heat dissipation. Good. Okay, so Haskell solution here, which is, so this is, I still remember the day that this message arrived from Phil Wadler. Phil Wadler and his produced, almost fully formed, the type class idea in a single email. At this stage, we've been wrestling with various solutions of this kind of thing, nothing very satisfactory. And then Phil dumped this in our laps, and we were just thrilled. It just seemed so amazingly simple and beautiful. Here's the idea, if you've not come across it before. We're going to give square, so I'll stick to numeric functions for a bit. We're going to give square a type like this. So this is similar to my plus here. We'll give it not for all a to a, but for all a that is numeric a to a. So you just read that as kind of like bounded polymorphism. For every type a that it's in the num class, it has type a to a. And so at least intuitively that makes some kind of sense. So sort should work on all types that are ordered. Serialize should work on all types that are showable or serializable. Member should work on all types that satisfy equality. Oh, I should have said, equality is so special in ML, it's a different kind of type variable. So is it tick A that ranges over equality types? Double tick A, right, there you go, thank you. So, but in Haskell it's just another type class here. So I'm hoping that at least at an intuitive level, the types are kind of saying what we mean a bit more precisely than they were before. And we're going to just see how it works. Okay? Any questions so far? Okay. Well, so let's see. These class things that these things here that I put in red, these are of course not built in. They're just declared. So here's how we declare them. So in Haskell, you declare the class num. This is just declared in a library. And you give, so you say A is a numeric type if it has these operations, plus, times, negate, and you give the signatures for those operations. And then you can say, that just, as it were, gives the shape of the operations that work over numeric types. And then for any particular type like int, we must say, oh, it is a numeric type. And the way you do that was with an instance declaration. So you say int is a numeric type. And in doing so, you must give a witness for each of these plus, negate, each of these things that we provided a signature here. You must just provide an instance. That is, you must say plus on ints is plus int. I'm assuming here that these are provided somehow more primitively, just the monomorphic operations over ints. So far so good? So that's kind of pretty simple. If you want, you declare a class that gives the signature of the operations, and an instance declaration just gives you the operations. Yeah?
Since we have one of them you have is ordinal, so we declare separately instance num word where?
Oh, wait, no, so here, this guy would be a different class, and order was short for ordered rather than ordinal. So this is a different class, and it would have operations like less than in it.
Yeah, but I assume you want int to be in both.
Yes, that's right. So I declare class ord, blah, 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 with greater than and so forth, and then I'd say instance ord of int. So completely separate from this, possibly even in a separate module. I'd introduce the class ord and the instances, right? And indeed, I can, if I've got an existing class like num or ord, and I declare a new type, you know, data, my type equals blah, 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 then I can make my type an instance of an existing class. Does that make sense? Yeah, good. Okay. And yeah.
So what if you want to use the operations on int that you're defining here, or like you want to build, so like any, like let's say if you want to like define order in terms of like area subtraction or something, you like sort of mix and say I'm going to use part of the instance for num for instance.
Oh, you mean what happens if in the ordered, let's write the, can you see this board if I write on here? Big class ord a where. So this is something like how ord works. It's got greater than, which has type a to bool. right? And I think you're asking, when I make when I make int an instance of this class, could I say something like greater than AB equals, well, let's see, if A minus B is sort of, so somehow, if I had is neg or something of B minus A. So here, this is one of these numeric operations from the num class, right? So it will only work if if int is an instance of num, but it is. So yes, I can use the operations, the numeric operations on ints if int is an instance of num when I'm defining the odd instance for int, and vice versa. Yeah, was that what you meant? Good.
Can there be implications between types?
You can beg your pardon?
Can there be implications between types, like if it's a member of?
Yes. So you can. So in fact, the odd class actually looks like, to be truthful, it looks like this. It says class eq a double arrow. So what this means is that every type that is an instance of odd must also be an instance of eq. And so eq here is called a superclass. So I should mention one thing. Look, you have to forget everything you know about object-oriented classes at the moment. So we use some of the same vocabulary with the same kinds of meanings, but if you try to identify them too closely, you will get confused. So as it were, try to wipe your brain from all that carefully acquired knowledge, just temporarily, then we'll reinstantiate it later. Okay, was that your question? Yeah. And when I make if I make int an instance of odd instance, I also say eq int where, and then I have to decide how to do equality. And these are separate. They don't, in fact, form one giant declaration, because eq is a separate class all by itself. Something can be an instance of eq, but not of odd, but not vice versa. Yeah?
Do you have classes that have multiple abstract types instead of just one?
Yes, so if you can, so this is, could you say class fugal AB where, blah, blah, blah? Absolutely, yes. These are not in the original Haskell, but it's one of the extensions that we've developed since, yeah. Okay, so we're looking at types, yes, go.
How do you deal with, if you have some generic, something like that, EK, or if you have some type of instance that's polymorphic over some other instance, and then
I'm going to show you that in a second. Yes, so it's kind of, like if I want equality over lists, you might think that would depend on equality over the elements of the list. I'm going to show you that in a second. Yeah, good question. Right on the ball. Excellent. Now, when people show me type system-y stuff, I always think, I wonder how that really works, right? So I always like to know what code is going to be executed at runtime, rather than knowing all this magic. So I'm a compiler writer kind of guy, so I'm going to show you the code that we generate to support type classes, because I think it helps with the intuition for how the source language works. So here, yellow is going to be Haskell source code, and blue is going to be a kind of decorated version of Haskell source code, or perhaps an intermediate language. So the first thing you have to know is when in the source language you write a function like this with this num_a arrow thing, and in the intermediate language this num_a constraint turns into an extra argument. So square here has one argument, but when executed it really takes two arguments, right? It takes this argument d and the original argument x. And what's d? You should think of d as kind of like a v table or function table or vector table of all the operations over int. It's called d for dictionary for kind of historical reasons. So it's an extra value argument, and it's a little record of, well, record of what? Well, a record of exactly these things. This defines the shape of the record. It has a field for plus, a field for times, a field for negate, and they all live in this little record d. So what does multiplication now do? What does star now have to do? It's just got to just index the v table. So star here is no more than a selector. So here's a data type declaration for num now, just declaring it as a single constructor with a number of function valued fields. And all star does is it picks out the, in this case, second field, the multiplication field. I mean, what could be easier than that, right? So I pass the v table as an argument, and then this star picks out, it really takes only one argument, picks out the function and applies it to x and x. Are we good? So really very straightforward. So there's a nice systematic translation from the source language into this runtime language so that there's no magic going on. It's just an ordinary functional language with kind of implicit parameter passing. So that's what class declarations turn into. A class declaration turns into a data type declaration together with the selectors. Instance declarations here, what do they turn into? Well, they turn into a record, a specific record. So here's the instance for numInt. So we get a specific record of type numInt that is, the mucnum constructor that we had here applied to just the functions for int. And what could be easier than that? So from an instance declaration, you get a value of type numInt. In fact, it kind of has the same type. You can think of it, if you think of this as numInt as a type, that is the type of the value over here. Okay? That's really all there is to it. It's kind of, whenever you see something double arrow, that means extra value argument. Whenever you see class, that just means record of functions. Then let's just look at something, I guess, a tiny bit more complicated. So if f here has type int to int, I declare it as having type int to int, and I call negate of square x. Now the square is this square, right? The one that takes two value arguments in the end. So square needs to be given as an extra argument. Well, what? Well, dnumInt this guy, because we're calling it at type int. And the same for negate. Negate was one of the operations in the num class, so it's just a selector, right? So it's kind of very uniform that we pass the dictionary both to the, as it were, primitive operations of the class, in this case negate, in which case it's just a record selector, or I pass it to compound operations like square here, which are then just going to pass it on to the primitive operations. So the vtables just travel around as extra arguments all the time. Make sense? So, and this composes really elegantly. So here's sum square, which takes, what does it do? It's square of x plus, it takes two arguments, both of type n here, returns a value of type n, and it takes the sum of the squares of x and y. What does that do when it's translated? Well, of course, because of the num n, it takes a d argument. What does it do with that d argument? Well, of course, it has to give it to square, because square, remember, here, took an extra d argument, so it passes it on to square, and it also needs to give it to plus, so that we can add them up, right? So it's a simple systematic translation. And so out of little overloaded functions like square and plus, I build bigger overloaded functions like sum square, and this just composes all the way up. Okay? Now, to your question about parameterized instances, supposing I want to take, here's the eq class, by the way, which does equality. Supposing I want to make lists an instance of equality. Well, clearly, I'm going to need to use equality over elements of the list, aren't I? It stands to reason, right? Because I'm going to, my equality function is going to be something like, well, if two empty lists are equal, and two conses are equal if the heads are equal and if the tails are equal. And that seems very, but look at these two calls to equals equals over here, right? This one here, x equals y, is an equality at type A, the element type, right? Whereas this one is an equality at type list of A. So this one is really a recursive call to this very function, whereas this call here is going to turn out to be a call to the vtable for, or the dictionary for the elements. And this all just turns into, when I said an instance declaration turns into a record declaration, well, in this case, it's a record function. It takes as just, remember, it goes ek arrow eq list of A, so ek arrow eq list of A. So it takes a record of equalities over, or equality operations over values of type A, and delivers a record, well, it's only one field in this record, of equalities over lists of A. So here's EQL, and now you can see that the two calls to equals equals on the right-hand side are really different. This one, on the head, picks out the equality guide from the element guide, and over here it's just a recursive call. Yeah?
What happens if you start making instances, say, EQ list of int, and you already have that one?
Oh, so if you have this one and you say instance eq list of int, now there's two ways, perhaps completely incompatible, of doing equality, and so the two instance declarations are rejected, right? So it just says overlapping instance declarations, bad plan, right? So the idea is for any one type, at least to a first approximation, there is only one dictionary, one vtable that will work. If you get two alternative ones, then your program's rejected because it's sort of incoherent. The different choices might give different answers on different days of the week with different compilers. Yes?
Isn't there a flag in Haskell for allowing that in the type of thing?
Yes, funny you should mention that. So well, it's not exactly in Haskell. So in GHC is a kind of, when I said crazy laboratory, so in GHC we'll let you shoot yourself in the foot. So we allow overlapping instances which say, oh, this instance is more specific, maybe for equality on ints. I've got a special, more efficient way to do it, right? In which case you say, I promise, on my honor, that I will, not be incoherent, that this specialized instance is better than the, right? And so then, so if you use the flag, we'll let you do that. But yes, but the whole business of is there a unique way to construct these dictionaries and the evidence is a big deal. And you want to know when you're stepping outside that safe boundary. Yes?
So what if I want to have, so I can view a pair of things as being ordered graphically either by the first or the second?
Yes.
So what if I want to have two different ordered instances for pairs?
This is the joy of lecturing to intelligent students. So this is, if you want two different orderings on the same type, you can't do it with type classes, right? What you can do is to, you can do something funny, which is to kind of wrap it up, right? You can say, if you have an AB pair, you could imagine applying a data constructor to it that turned it from an AB pair into, my funny pair or backwards pair. So let me give a data type declaration. It's a bit of a contrivance, right? I won't deny this, but this is what you have to do. So, like most programming languages, there are compromises, and this is one of them. So if I say data back pair, which I'm meaning AB equals, I don't know, BP of, and I'll just put, so all I'm doing is I'm wrapping this in a little constructor. Now I can say instance ord of BP, back pair, BP AB, and now I can order it the other way around, right? So in effect, I'm forced to sort of change the type in order to get a different ordering. Now, if you were doing a sort of ML functor kind of thing, you could have more fine-grained control, but Haskell doesn't give you that for these instances. So it's very, very convenient when you've got one thing to do for a type, and very, very inconvenient when you want more than one thing for the type. Yeah. Yes, in the middle here. Yes. So we're going to talk about new types a little later, but you'd be better off doing this because then there's no overhead from this BP stuff, right? It's a sort of zero runtime overhead thing. We'll come back to new types a little later for anybody who hasn't come across them before. Right at the back.
So are these B tables used at compile time or at runtime?
So yes, good question. So these things, this is a D argument, right? Is it passed at runtime? Yes, it is, right? But well, why? Well, let's look at our friend SumSquare, for example, right? If SumSquare claims to be callable on any value of type n, floats, doubles, lists, who knows what, anything that is a numeric class. So in order to be polymorphic, you have to give it this guy, right, to know what to do. But you might think, well, look, could I make a specialized copy for it? So if I see it called at type int, I'll specialize SumSquare to be int to int to int. And if I see it called at type float, I'll specialize it to be float to float to float. Because once you know the type, then because there's only one num dictionary for float, as we've just been discussing, we can make one specialized copy. So in fact, a good deal of what GHC does is to make specialized copies of overloaded functions so that you get the nice tight machine code you might hope for. So it's kind of like saying, you write the boilerplate code once and the compiler just cranks out copies of it. That's the idea.
So in effect, there's no sort of multiplexing runtime?
Well, it depends. So sometimes you really might want this to be a polymorphic function, right? There really might be situations in which you could not specialize it because it's stuffed inside an existential somewhere, or it's in some very polymorphic situation that you've not specialized. So the idea is the overloaded one with all this runtime dispatch is always there for you, right, in case you need it. But we'll crank out specialized copies for the cases when we can monomorphize the program sufficiently. Right? Sometimes you can't. Haskell has polymorphic recursion, so you can't even if you have the whole program, you can't necessarily eliminate all polymorphism. Cool. Okay. So where are we? That's the idea of instances here. One last thing is that in the num class, there's a funny operation, this from integer one, that takes an integer and returns an a. Now, why is this funny? Well, why am I drawing attention to from integer here? The shape of its type. Yes. Right, we're dispatching on the return type, not on the argument. So there isn't an argument of type A to even look at, right? So, but it works out perfectly fine with this dictionary parsing thing. From integer takes a dictionary, just like anything else, and it picks out the from integer method and applies it to the integer 1. So it's rather, we can dispatch on return types just as well as argument types, and that's very, very convenient. And it's very important too, practically. This was a huge thing when we were first doing this at Haskell. Increment here, x is x plus 1. What is this 1? And it would be very, very annoying if that always meant int or integer or float or double. The fact that it can mean 1 of any type is a big deal. So in Haskell, when you write a literal constant like 1, that is simply shorthand for from integer applied to the integer. So this 1 is the honestness integer 1, right? Whereas this one is is short for that. That make sense? So it's very important that literals have this sort of special status. They fluff up rather like plus does into constants. It's sort of, literals are always special in some way, right? They have special syntax. Yeah.
Are instances mandatory in Haskell?
Oh, instance is mandatory. No, you can write a program that has no classes and no instances at all.
Well, you have classes. And
oh, if you have classes but no instances, you can't use them.
The instances are necessary.
Well, you couldn't actually. So if you have a function, so if you have a class with no instances, I could write a function like my friend square again, right? I could write this, but I couldn't call it. So yes, go and be my guest, right?
I was trying to. I know we'd eventually descend into some sort of hell in which I'd have to take everything on faith and nothing would work. But
no, it's not that nothing would work. It's just that you would not. How could you call num square? Could you call it on a float? Well, no, because then you'd need num float, and you haven't got an instance for num float, right? Because whenever you call sum square, I'm going to say the compiler has to run around and find a num float record somewhere, and it can only do those for instance declarations.
okay.
That's its business in life.
Gotcha.
Yeah. So for this, and when in this instance declaration here, if I need equality on lists of int, the compiler says, oh, how can I find equality on lists of int? Oh, look, I've got this instance declaration. So it says, oh, let me use that. Oh, now I need equality on int. Oh, that's good. I have an instance declaration for eqint. So it does a little bit of a sort of backward chaining kind of proof to generate this evidence for you. And if you have no instances, it can't do that.
So there's something that exists intrinsically, you have to define instances. I was saying like
Now, if you-
plus, like for say you have something hard coded such that plus is plus for integers in a certain context, but Haskell seems a little more free form than that. Allowing you to set up instances.
When there's floating point plus and integer plus, right? When you actually get to know the class.
Yeah. So somehow if you have a class but no instances for it, then any function that uses methods from that class will be uncallable, right? Except from other functions which are also overloaded over that class. So in the event, you can keep writing more functions, but you could never run them until you provide an instance, which seems reasonable. Because after all, they're not. It's only a compiler. It's not magical. Okay. So let's see. So this all started just for equality and numerics and sort of read and show. Right, that was really our motivating examples, which seemed painful. Then we kind of had this Damascus Road experience when we figured out about monads. And monads fit into this beautifully, right? So I don't want to stall on monads here, but here is the monad class. And what's fun about this is that this time we're overloading over this type variable of m here, and m, look, is a higher kinded thing. It has kind star to star. So that turned out to be really important too. There's a nice fit between type classes and this higher kinded stuff that I'll talk about in the next lecture. But having got these basic ideas going, then it turned out that there was an enormous, it was kind of like lighting a pile of gunpowder. The sort of creative world went out there, and they just went on and on and on, generating more classes. So nowadays, most Haskell programs defined several new classes all of their own. So it was an enormous sort of, it opened up a new area for sort of program structuring and creativity ideas. It's hard to explain, so I'm going to give you an example. So I'm now kind of moving in one step from basic numerics and read and show up to the coolest example of type classes that I know, right? So at this stage we may have to pause and just go a little bit slower, but I would like you to pay attention here because this is a slide you are going to want to remember, right? And I say this because it was invented by John Hughes and Kuhn Klassen, not me. So this is quick check, and some of you will have come across quick check. The idea with quick check is that you test your Haskell code by writing functions which describe properties of your code. So prop rev here has type list of int to bool, and it's testing the property that reversing a list and then reversing the result gets you back to the original, right? So prop rev should always return true, right? No matter what list I give it, finite list. Prop rev app takes two lists, and it says if I append the two lists and then reverse the result, that's the same as reversing the second and reversing the, okay? This function also ought to return true. So now, what I would then like to do is to run a test program, that's quick check, over these functions. And here's in my interactive read eval print loop, here's the prompt. I call quick check on prop rev, and it says, yes, I generated 100 random tests, I applied prop rev to 100 different lists of ints, and it always returned true. And then you call quick check on prop rev app, and it says, yes, I applied prop rev app to 100 pairs of lists, right, of ints of various lengths, and it always returned true. Now, what's weird here? Tell me what's strange about this slide. Somebody who hasn't already spoken. What's strange on this slide? Two different types. So quick check here, it's taking an argument here type list of int to bool, and here list of int to list of int to bool. So clearly, quick check can't have either of those individual types. So quick check somehow has to be polymorphic. And somehow it's managed to work out the arity. This function has one argument, this has two. It's worked out its arity and futzed up two lots of argument lists. Isn't that rather amazing? Well, how did it do that? Well, quick check had better have a polymorphic type. So here is quick check's type. For all A, testable A to IO unit. The IO unit bit is so that it can do input-output and actually print these messages. So don't worry about that part. Just concentrate on the A arrow. So take an argument of any type A that is testable. All right? What is this testable class? Well, here it is. A value A is testable if I can take a value of that type, let's say it's a function, and a random number supply, and return a Boolean that says whether the test succeeded or not. So the idea is I'm going to take the function, using the random number supply, build a random value of that type, apply the function and see whether it returned true. All right? That's what testable is supposed to mean. But this A here is meant to be, could be a function of one argument or two arguments or 100 arguments. Who knows? We'll see. Is that so far so good? Just the intuition of what this line means? All right, now I'm going to need one more class, this arbitrary class, which says, because I need a way to make up random values. So I need a way to make up random integers, random floats, random lists of integers, random trees of integers, all right? Well, that's just an example of the same kind of overloaded function we've been talking about this whole lecture. So here's so it clearly needs a random number supply. Remember, Haskell is pure, right? We don't futz around with side effecting random numbers in the background. No, we give it an argument here. So it takes a random number supply and delivers a value of type A, all right? Now, let's write some instances for testable. So bool is the kind of base case. This happens if once you've exhausted all the functions of your argument. I'm expecting if it's a nullary function that it takes no arguments but returns a Boolean, then we get down to this base case. So how do we test that? Well, it's pretty easy. We don't need the random number supply. We just return B. All right. But now here is the amazing code. So these 4 lines of code deserve a sort of little gasp of awe. I thought this was amazing when I first saw it. What is this saying? This says A arrow B, a function from A to B, is testable if what? If B is testable, that is, remember, typically functions go list of int to bool or something. So if B, that is the rest of the function, is testable, and A, the argument, if I can make up random values of that type, right? So that means arbitrary here. So that's why the argument type must be, I must be able to make up random values, and the remaining function is testable. Okay, so how would I then say test, look at its type? It takes the function of this A arrow B type and a random number supply R, and what have we got to do? Well, we've got to apply the function to a randomly chosen value of type A. Where can we get a randomly chosen value of type A from? from RB, of course, that this friend here, we've got to apply him to a random number supply, and then we apply F to him. What could be easier? What is this R1? Well, I do need to be able to take my random number supply and split it into two, right? So I'm assuming that random number supplies come with this function. So I take one half of it and I give it to RB, and that gives me a random value of type A. And what's the result? So F applied to RB of R2 is of type B, right? Because this is F is type A arrow B. So if I apply it to one argument, I get something of type B. Happily, B is testable. So all I've got to do is apply test to it. And that's all there is to it. Nothing up my sleeve? That's it. Yeah?
So I assume random supply is a function that's defined elsewhere.
Rand supply, imagine it is an infinite tree of random numbers. That's probably the easiest thing. It's not a function at all. It's just a value.
It's a value, but it's okay.
Think of it as an infinite tree of random. So Haskell has all these infinite data structures. It's just an infinite tree of random numbers. Wherever you look, there's another random number.
Okay, and
So I can split it in half to get two trees, and I can look at the random number at the root, and that's random.
yeah, and so for lists, it seems like for like say a list of integers, for one thing, everything here requires that integers sort of determine the randomness of structure, right? Because
Well, so are you asking how would I make an arbitrary instance of int? I haven't shown you the arbitrary instances, so if I said instance arbitrary int, what would I do? Is that your question?
well, I'm just asking, does it have to be of something that's integer?
There's no integers here.
Well, you said rand supply, I thought it was a list of random.
Oh, rand supply is a list of random numbers, right? Let's suppose that they're ints, but maybe it just supplies one bit at a time. Perhaps you say rand supply, you can take a random supply and get one bit out of it. So then you can split it to get as many bits as you like.
Are you going to do an example of that?
No, I'm not going to do an example of rand, but I'm hoping that you can guess that if from one of these rand supplies you can both get two more and get a single bit, then I can construct a bit string of arbitrary length at any moment from a random supply.
Sure. So I was just thinking, like, how would you get a random list? I think first you would need a number that.
How would you get a random list? Good question. So how would I make the arbitrary instance for lists? Very good. So what is that going to look like? Well, so it's got to be, we've got to write a value for RB, which has type rand supply to list of A. So you might try something like, well, if the random supply, let's get one bit out of it that determines whether I'm going to do cons or nil, right? So to get one bit out of the random supply, if it's 0, I'll do cons, and if it's 1, I'll do nil. Right? In the nil case, I'm done. In the cons case, I need to split the random number supply to make an arbitrary head, and then also to recursively get an arbitrary tail. Now, in fact, if you read the quick check paper, there's a great deal of cleverness that goes into building good instances for RB to make nice, to make short lists come first, and to make the sort of test space be well populated. And in fact, they have a little domain-specific language that's specifically about generating well-shaped random values that fit your particular application. But I'm not going to go into that here. But it's a good example of why it's a good idea to be able to write your instances yourself. But sometimes it's domain-specific. Yeah?
Is it one problem with this that you are tied to one testing strategy for each type?
Yes. Again, this is just like we were saying over here. Once you fix the type, I'm going to say if it's a list of int, then I'm going to only give you one arbitrary way to construct list of ints, and you have to do something like this trick to get around that. Yep. Same question, same answer. There are limitations here too. Yeah.
In this case, I could just split my tests into different modules, each with their own instance.
Yes. So it's not very good practice to have the same type with different instances in different modules, but you kind of can do that. But I would probably do something more like this myself, personally. Yeah.
Is it decidable whether a type has an instance?
Is it decidable whether?
Whether a type has an instance?
Is it decidable whether a type has an instance? Well, that's like saying, is it decidable whether I can write a compiler for a language? I mean, you write the instances. They're not made up for you, right?
It seems like there might be cycles.
Oh, could there be so? Right. So you're saying, supposing I wrote something like, if you said something like, instance eq list of A arrow eq list of A, where blah, blah, blah. So I'd say, yes, I can make an eq of a dictionary if I have an eq list of a dictionary. And I can make an eq list of a dictionary, so you could imagine this could go around forever, right? But this is the language rules this out, right? Unless, of course, you give a flag to the GHC. Every question has an answer that includes, unless you give the flag to the compiler. But so this is, in the base compiler, this is ruled out. So then, indeed, the process of figuring out dictionaries is always decidable. Yeah, in fact, it's finite in a very straightforward way. It's sort of like structural induction, structural recursion. Okay, so I think this is very beautiful, but it's just an example of the kind of amazing stuff that you get once you unleash people with type classes. I don't quite know what it is, but notice too that this RB is another example of that from integer. We're doing dispatch on the result type, and that was crucial. You could not do this without dispatch on the result type. Okay, here is a little picture of what happened when we invented type classes. So we're sort of wildly enthusiastic to begin with, and then I started to implement it. And the stuff you were talking about efficiency really bit. So our first implementations were really slow, and it took quite a long time to make all the specialization work well. But now we think that every schoolgirl should have this stuff. It's just too much fun. And it's also served, back from those initial days, it served as a kind of seedbed for an enormous sort of efflorescence of other ideas that have built on top of it. Few of which I'm going to talk about. Well, I'm not going to talk about any of them today. I'm going to talk about some of these pieces a little bit in subsequent lectures. But it's an example of one of those, the kind of Phil and Steve in their initial idea. It's very seldom in computer science you can really point to that was the moment at which a whole chunk of stuff opened up. Of course, there are ways in which we've been discussing type classes are not the right thing, and there are other approaches to these kind of things, but nevertheless, it's proved a very, very fruitful area. Okay, so I want to say something a little bit about the relationship between Haskell's type classes and object-oriented type classes. So this is so now you can, as it were, remember again how object-oriented classes work. I've got a few observations about the relationship between them. First thing to do is what many of you will have worked out already, which is that a Haskell type class is more like an OO interface rather than an OO class. So in Haskell you say, here's the show class, it has a single method with show to string, and in Java or C# or something you might say an interface, showable, right, which has a method here, and then you can give f, you can say f's argument type is showable, right? Anything that satisfies that interface will be okay as f's argument type, and that has something of the same flavor here. But there are two differences here. One is that with Haskell it's easy to give a function many type class parameters, right? So here this has two. So this works on any a which is both numeric and showable. There's really no difficulty with that. That was right back in Haskell 98. But this is not so easy in an OO language, except, of course, that OO languages have grown extensions subsequent, in later years, they've discovered, oh, this is a very useful thing to do. So now you can, say, have an interface that's a union of two other interfaces. But another difference is that in Haskell, it's really very important that if I define a new class, I can make an old type, like int, an instance of it. If I declare a new interface, it's not so easy to make old classes satisfy that interface. Again, this is something that I think has been fixed in more recent versions of OO languages, but this is one way in which Haskell is quite good with retroactive modification. I'll show you in a second a way in which Haskell is much worse at retroactive modification. So I just want to fix first that Haskell class OO interface is a good first approximation, not Haskell class OO class, not at all. Okay. Second thing, that as somebody's remarked already, we're really doing type-based dispatch, not value-based dispatch. And here's what I mean by this. It's kind of tempting to think that this is a bit like an object-oriented thing in which I look at I could have a V table attached to A and dispatch on that. But as we've seen, we sometimes dispatch on the return type. Here is read, which is one of these something to A functions. So here we're dispatching on the return type. We still pass two dictionaries for read A and num A. And this is all just perfectly fine. There's no difficulty with this. And notice this even applies, this negate guy, he looked perfectly ordinary, but in fact this negate guy is applying to a value that we've just built right here. This guy is of type A, right? We built him right here from a S, which is a string, all right? So very important that we're doing type-based dispatch. So in a way, it's more like type case. So here's in a parametrically polymorphic language like this, we have these for alls. And if you could imagine that you pass the type A as an argument, right, in which case, say you pass T and X of type, well, maybe I should call it A and X of type A, and then maybe I could scrutinize the type itself. And there certainly are languages that support type case, so they have to, then you have to pass the types around at runtime. Here we don't pass the types around at runtime, we pass just these dictionary things. So instead of passing a representation of the type A around, we pass a method suite of the C classes methods over A around. Does that make a difference? Do you see the point there? So in some ways this is more universal, because if you pass just one type representation, you could dispatch and do anything. Here we're deliberately limiting it, saying no, you can't do anything to A's, any old serialization, just the things that are in C. Right? So it's kind of bounded polymorphism. Okay? So here is some an example of how this of a type class that gets you quite close to this type case stuff. This is the typable type class, which we can write already with what we have today, with what I've shown you so far. So it looks like this. A type A is typable if you have this function typerep, which goes A to typerep. What's typerep? Think of it as a runtime representation of a type. So here is a crude version of it. It's just a tr, that's the data constructor, string, that's going to be the type constructor, and list of type reps are the argument. So these are just monomorphic types. So if I call type rep of foo is a string. In Haskell, strings are just lists of characters. So what's the type of a string? It's a list of char, right? So did I get this right? Yes, I did. Yes. So it's just and this isn't really going to be a string in reality, but you could do something like this. Does this make sense? So you can easily get from a value to a representation of the value's type. And do we get that from the value? No, we don't really get that from the value. Look, here's an instance of typable for int. Well, we don't need to look at this a value, because we can just say it's an int. Right? That's its type representation. What about lists? So it's going to be something like typable a to typable list of a. So you think, all right, so it's going to have list as its type constructor. But what are we going to put inside here? So I've started to write this, but this is not very cool. Why is this not cool? Somebody who hasn't spoken before. This is not at all good definition. What happens if I give it the empty list? So if I say, what's the type of the empty list? Oh, smack forward, what's this thing going to do? It's going to collapse. And if I try to write type rep of empty list here, what would I say? Or maybe, so it's still a list of, well, what? I don't have anything to take a type rep of, right? Because it's empty, right? But my mistake is looking at this at all, right? Here is a better way to write it. So I write type rep of, well, anything at all, and when I make my recursive call here, I'll just pass bottom. So remember Haskell lazy language? You can undefined just means bottom. It just is a computation that diverges. And I want undefined of type A. So this is a scoped type variable here. This just says a value. So I'm always going to apply type rep to bottom, but it's a bottom of the right type, namely, in this case, A. Now, and let's see. So this value argument here is never actually looked at. So why am I passing it? Why am I passing it?
I just had that question.
Well, so you can answer. So supposing this just said, supposing I said type rep colon, so type rep here, colon, colon, type rep with no A arrow. Now, so then then my function type rep would have a type like this for all A, typable A, arrow, type rep. Right? So in here, then I could just write tr of list singleton argument type rep, right? Now, but put yourself in the position of the compiler. What dictionary are you going to pass here? Yeah.
It's because you can't explicitly refer to the dictionary that you're
That's right, all these dictionaries, those red guys are being passed around kind of implicitly. I don't have a way to say type rep applied to the dictionary for typable at type A, right? I don't have syntax for that. You could imagine inventing syntax for that, right? But Haskell, as she is defined, doesn't have that. And so I have to have a way to say, which type do I intend to call type rep at? So this argument here is a kind of proxy argument. It's never looked at. It really plays the role of a type argument that says which type to call type rep at, and therefore which dictionary to construct. And that's all it's doing, right? So it's a kind of idiom. And maybe it would be nicer to have explicit type application like Agda and Coq have, and then you wouldn't need to say that. Yeah, right at the back.
Is there any way to sort of guarantee that argument type reps will never be evaluated? No. So it is just an idiom, right? I thought you were going to say, is there any way to guarantee that I don't write something bogus here, like int again? So in fact, this type class does exist, and all the instances, in fact, in GHC's implementation are mechanically generated because we're going to trust these type reps. I just want to show you how they're generated. So we trust them, but partly we trust them because they're going to give us type reps that are accurate, and also we trust them because then they will never look at their argument, because GHC generates the code, and of course, there's no bugs in GHC. Yeah.
So just to be clear, the undefined is just a dummy value that's there for the sake of generating a dictionary.
Yes, that's right.
Okay.
Yes. So the argument here. In fact, this argument is always the argument that's passed is always a dummy value. It's never looked at, and undefined is just a convenient one. And it's defined, undefined is not built in, it's just defined by undefined equals undefined, with type for all AA, right? But by constraining its type here, so that's why I call it a proxy argument, because it's really a value level proxy for a type level argument. Yeah?
Would you keep the implementation in the instance we were doing before and then pattern match in the element?
You mean like I did here?
Yeah.
If you pattern match on it, then of course, this idiom won't work, right? Because when you...
But you will use that undefined in the case where you have empty.
Oh, yes, you could, yes. Well, so you could then say type rep empty list equals then tr list, and then you could use undefined, right? But that means that this instance of type rep is no longer lazy. So if somebody else calls this instance of type rep on undefined, like if I was taking a list of ints, now you'll get bottom, which is why your friend on the back said is the way to guarantee that it never looks at its argument. But we are rather relying on it when we call it in this way here. Okay? Anyone else? This kind of, yeah.
Why couldn't you just annotate the calling of type rep in the last line with the type?
Oh.
Then you wouldn't need undefined and you would omit the dummy argument.
Wait, so you say give it no argument at all?
Yeah.
So make it like this?
Yeah.
Right, well then, what would it mean if I said type rep? So, you need scope, you could, let's see. So what would you say here, right? You could say it has type rep. But that doesn't help us because we still don't know what type to instantiate it at. This is a call, by the way. So this is something like, list. This is in this list argument where we said tr list, right? So we could do this, but we still don't know which type type to call it at, right? And if we said for all a typable a, or even if we just said typable a double arrow this, so now we're getting close. Maybe this would just about work, but this. I think this is more convenient in the end. I need to think about that. Yeah, with a scope type variable.
Could you make type rep a phantom type?
Ah, yes. So maybe you want to say type rep has type rep of A. Yes, so parameterize type rep in a phantom way. That has a whole raft of different consequences. Like then it's difficult to make a list of type reps because they're all of different types. So you're right. That's another variant of the whole reflection story. Yeah.
You could replace the argument of type rep with something like that, a phantom argument.
Oh, could I replace that with a yes? In fact, the real one. You're saying it doesn't have to be a value of type A. It could be something like proxy A.
So in fact, the real type of type rep these days is for all P of A, arrow type rep. So for any P, so like list or proxy, or so it's that turns out to be quite convenient, especially when we get to higher kinds, which we will on Thursday. Yeah.
So does this mean that Haskell doesn't have an empty type because bottom is type?
It does mean that Haskell has no empty type. Yes, yes. Even bottom is inhabited. So if you say data T equals T, it's inhabited. It's got one. Yes. Sorry. Every type is inhabited by bottom. Yeah. It does. So. Okay. So that was it for type-based dispatch. So I just wanted to make a few remarks about generic versus parametric polymorphism before I sort of wrap up here. So, and here's a kind of picture that I've sort of grown in my mind, which is this. Look, so object-oriented languages and parametrically polymorphic languages grew from sort of in different language traditions, but with one common idea, namely polymorphism, in the sense of a single piece of code that works on a variety of values. So in the case of the object-oriented culture, right, something like cost, which has type car to int, is polymorphic in the sense that it will work on cars and on voxels and on Fords and on all sorts of cars. Okay, so that's a kind of polymorphism. Over in the ML world, and I'm speaking ML, but this is when talking now the early 80s, there was parametric polymorphism, which said reverse works on values of many types, so many kinds of arguments, lists of ints, lists of chars, and so forth. And so these were two different ways of obtaining polymorphism. Now, they don't overlap very much with the sort of very basic object-oriented style polymorphism and the most basic find of parametric polymorphism. They seem to be not quite orthogonal, but close to orthogonal, right? So what then happened is that each language culture here became envious of the other, right, and started to hash include stuff from them. So let's just look a moment at the sort of different consequences of these decisions. So let's see, Haskell, beg your pardon, this decision here is to do with subtyping. The reason that cost works on voxels is because voxel is a subtype of car, right? So inherently subtyping involved here and parametric polymorphism or generics over here. So in Haskell, for example, no subtyping. So if I have a tree which is either a leaf or a branch of trees, there's no way to say that this will work on any subtype of trees. For example, maybe trees that are guaranteed to contain leaves. The argument to F has to be exactly a tree. The way we get to operate on arguments of various types is by type classes. So there's no subtype stuff involved. Now this is, in some ways, not cool at all. The amazing thing about object-oriented languages is that you can retroactively extend them. So here, let's take a concrete example. If I write a function with type tree to int, and then I'd like it to work on some other argument that isn't exactly a tree, but sort of is tree-like somehow, well, in an object-oriented language, you can often do exactly that by defining the new class for your tree-like thing, and and you give the methods for the function on that new class. But here, I can't do that. I can only do that if I anticipate this when I write f. And I write f in this overloaded way by saying it'll work on any tree-like argument. See what I mean? So a very cool thing about object-oriented languages, they allow this retroactive extension. And here this doesn't, you have to anticipate in Haskell. That's I think is a shortcoming. But it does come with, there are other consequences too of these choices of subtyping versus parametric polymorphism. Here's one. One is that in the Haskell world, typically, and the ML world, of course, everything is implicit, and type annotations are, maybe never needed. In initial ML, it was never at all. These days, certainly in Haskell, type annotations are occasionally needed. And again, the starting point in the OO world is that everything was explicit. Every binder carried its type. These days, languages like C# and Java allow you to omit the types on some variable declarations, but at least initially, everything was completely explicit. Every binder had its own thing. Do you see the difference? Now, why did that happen? Was this just a cultural difference? It was not just a cultural difference. It was kind of forced on us, right? Because if you have parametric polymorphism alone, then as you do type inference, you generate equality constraints that you say this type must be equal to this other type, right? In the world of object-oriented programming, when you do type inference, well, because even in an OO language you are doing type inference, but you've not decorated every subterm with its type, right? So there is local inference going on in every OO compiler. But that local inference is generating subtype constraints. It means that if you call a function applied to an argument, the type of an argument must be a subtype of the type expected by the function. Does that make sense? So everywhere the inference engine is proving subtype constraints. Now, the thing is that equality constraints, we have a principal solution, right? We just call unify, and we can find the most general solution. Subtype constraints have no such most general solutions, and so it's much more straightforward just to declare the type of every binder. So it's a sort of technically driven thing, but it's turned into almost a cultural thing. We almost take it for granted. Let me show you one other difference, is that in the object-oriented world, because of the subtyping thing, look at a function like increment, which takes, let's say inum is the numeric interface. If it takes something that satisfies the numeric interface, then of course it can take anything more specific than that, but it will return something satisfying the inum interface, but you cannot promise any more. If you give it something very specific like a float, you can't guarantee you'll get back a float, you just get something inumish. Well, of course, with this type, you can say, if you give me a float, I'll give you a float. If you give me an int, I'll give you an int. If you give me a matrix, I'll give you back a matrix. Does that make sense? So that you kind of maintain precision. So when you say x.inc, all you get is an inum. When you say incx here, you get a float. So I've always wondered, why is it that in OO languages this is not a major pain? Yes?
For Java, can't you do generics that you give inum an extra argument?
Yes, you can. So this is so important that object-oriented languages have retroactively, as it were, in the language design, done this. And some of you will know more about this than me. But even before, this is relatively recent, right? This is since 2000, those who know, yeah? So before that, why was it they could get away without it? Because it seems so basic in Haskell not to lose this. And I think it's because OO languages are mostly imperative, right? So here, if you do x.setColor and x.setPosition, then x doesn't change its type, right? Because we are side effecting x, and x has a stable type throughout. But in Haskell, you would say something like set color of x, and you would get back a new button or canvas. And then you would say set position of that, you get back a new one, right? So in a functional world, you have lots of functions like this, and not so many that just side effect things. And I think that's why OO languages have managed to get such a long way without this. Yeah.
What does result contravariance mean?
Oh, it means that that here. What do I mean? That the result will support inum, but perhaps no more, right? It might be you might get a floating point number out of here, but you won't. All you can know is that it'll work with inum. That's all I meant. Maybe I even used the wrong word. Yes.
But isn't it that different because in OO we expect to have dynamic semantics? I mean, you could downcast an object.
Yes. So you can do runtime type tests. That's what you mean. Yes, you certainly can do runtime type tests. But what's tantalizing here is that if the increment on a float really does give you a float, there's no need for a runtime type test. It's a sort of runtime type test you know will succeed.
Because only because you want to take that as a static type.
Well, yes, you might like to give it to a function that really expects a float. And you might like to know statically that downcast cannot fail. Well, okay, you could, but isn't it a bit tantalizing that there are these tests that you know are not going to fail, but you have to make anyway, and you kind of have to execute. So, and in fact, so tantalizing that OO languages have invented something very like this. I think it's called constrained generics. Am I right? Those of you who know this stuff, right? So I'm a bit out of my depth here in this OO land, right? But I think this is the way it looks like in C#, and it gets you essentially this type. So you're looking a bit blank as well. No? So this is why I'm not quite sure how widely used this stuff is, but you can do it these days, both in Java and C#, I'm told. Now, last piece of what happens if you combine this parametric polymorphism stuff with subtyping is to do with variance. Now, parametric polymorphism is so useful that object-oriented languages adopted it quite a long time ago. It was called generic Java, and now it's just called Java. C# always had parametric polymorphism. In the OO world, it's called generics, I'm sure you know. But as soon as you have generics in an OO language, you need to have variants, right? What does this mean? So here's I enumerator, right? And here's a declaration of I enumerator. I think this is C#, right? And this is saying this is only legal if this T guy is returned by method. So here's T current here is returning a value of type T. It's not okay if I enumerator takes if the methods of I enumerator take arguments of type T. Why do you have to specify this out thing, right? Which is the variance control? Because here I want to be able to take I've got a method which takes an I enumerator of a control, and I want to pass it a value whose type is an I enumerator of button. Why is this okay? It's okay because button is a subtype of control, right? But it's only okay if I enumerator uses these T guys in the right way. If it passes them in, it wouldn't be good for it to be a subtype. It would have to be a supertype. You see the problem? Right, so if current, if it returned an int and took a value of type T, then it would need to be the other way around. So you have to have these variance annotations to deal with the combination of subtyping and generics, right? And that's a bit tiresome, and people who are doing this stuff grapple with this all the time. So, and it gets even worse if you want higher kinds. Remember this monad class here, this M guy? So he has kind star to star. And now, is that a covariant type? So M ranges over type constructors, like I enumerator or list. So what about the variance of M itself? Right? Is it a covariant type constructor or contravariant type constructor? Or maybe you'd like it to be polymorphically variant. So there's a sort of ghastly swamp that reaches out its sticky fingers to suck you down. And Scala can do this kind of thing, but I need to talk to Martin Odersky about this. I believe that he sort of retreated gently from this because the sticky swamp was reaching out and too far. It's very, very the combination of parametric polymorphism with full-on subtyping is hard, right? That's the message I want to get across. I think only Scala has really bitten this bullet hard, and Scala is a fairly complicated language. It's an incredible achievement, but it is tricky. So here's the overall picture then, right? So with all this envy of each other, right? The ML, well, at least Haskell here, we had these type class things which allowed us to cover some of the same territory as OO stuff. Meanwhile, the OO folk have sort of slurped in generics and constrained polymorphism and all of that. And now the two really overlap quite a lot. And when you have two complicated things, right, that do mostly the same thing, so the extra delta of added the second complicated thing is only a little bit, you've got to wonder, is it sensible to have them both? Well, it's pretty clear we're not going to have subtyping without parametric polymorphism, right? The object-oriented languages adopted parametric polymorphism. So here's my sort of closing sort of question is, if you're going to have a language with both, maybe it's time for object-oriented languages to abandon the scaffolding of subtyping and embrace parametric polymorphism in its true glory. And just because the combination is hard. Right. And so I don't know the answer to this question. I don't think they're going to abandon it anytime soon. But I did take the liberty of putting this up at eCoop a couple of years ago, and was not torn limb from limb, which I fully expected to be. But it's kind of tantalizing, isn't it? And I do worry about the intellectual complexity of combining subtyping with generics. For my money, my personal conclusion is parametric polymorphism without that subtyping, as it were, doesn't pay its way in the end. But having said that, of course, you can do things in OO languages that make me salivate. How can I do that? But sometimes you have to stick to your guns and wear the hair shirt. Yes.
So I don't use languages with subtyping, but what's the most compelling example that someone's giving you?
What is the most compelling example of language? So, well, one superficial thing that I really envy is being able to say, x dot and then have a list of functions that drop down. So kind of, that's so cool. Whereas we go function applied to, and we have to think about what function. So maybe we should invent reverse function application. That'd be useful. So being able to this business about retroactive subclassing, so you can have existing functions that take things of a certain class, and then you can add methods to them and they still work. And also having heterogeneous collections of things of various types. And if you look at the collections library, I think the collections library is a good place to look. Scala's collection library is a sort of tour de force, or the SDL library in C++, an amazing sort of testament to the power of what you can do with ingenious use of subclassing. I don't presume to understand the sort of the deep thought behind that, but I have to respect it. And I think our collection story is less rich than that somehow, in ways I'm not sure I could really articulate very clearly for you now. Yeah. Yes. So how would you add a float to a double? Very good question, and one that I'll tackle head on in the next lecture. Excellent, I'm glad you asked that. I'll pay you later. Yes?
This question came up 2 times, like we wanted, in the first example, a different ordering, and your solution was to define a new pair class.
Oh, yes.
And this also came up in the context of lists. But the problem I see with that approach is when you define your new list just to get the different
ordering.
Yeah.
Mm-hmm.
You will have like duplicate all the other code that was written for other things to do with lists, and is that not a problem?
Yes. So you're nibbling away at this question about whether we need to make the same type an instance of the same class in more than one way, right? Different ordering on lists. And all I can say is that it seems to be less of a problem in practice than you might think in theory. This is not, so I hang out on all the Haskell mailing lists, and maybe they're just inured to this, but there are not many cries of pain about this particular thing. Now, you were saying, does it, would you have to duplicate all the functions on lists? Well, maybe not if you could quickly go back to list, reverse it, and then back, which would be inconvenient. But actually, usually what happens is you do the sort of converting into the funny type just before you call the operation that you want to work in the funny way. And again, Haskell has the Haskell libraries, because it is inconvenient to do that, as well as sort with type list of A to list of A. It also has a function called sort by, which has an explicit function of type A to ordering to list of A to list of A, precisely so that you can explicitly control it. So when it's frequently the case you want, then we just abstract over the function explicitly rather than implicitly using the dictionaries. So it's not perfect, I grant you, but it's perhaps less of a problem in practice than, I mean, so there are some people like Edward here. Edward, how often have you stumbled over this in practice? Oh, you weren't paying attention. Ha ha. That's because you actually know all of this. So it's making the same type an instance of the same class in 2 different ways, like the ordering of list things that we were talking about over here. Has that ever bitten you? I mean, you've written lots of Haskell code.
I occasionally need it, but then I just mute type it.
Right. So you're right. So it's one of the, yeah. I see he's corroborating. Like, well done. I'll pay you afterwards too. Yes, at the back. Yes.
And so doesn't that, in a sense, undermine the...
Well...
It's sort of a work on the side of all...
Yes, that's right. So the very existence of those by functions is an acknowledgement of a shortcoming of the whole approach, right? But it's kind of the expression problem, yeah. So if we knew a way to solve all these problems at once and get all the convenience of Haskell, then we'd adopt it. But we don't. At least I don't. So we have the by functions as well, and it's not a perfect world. But at the same time, it does seem to be in a very, it may not be perfect, but very, very fruitful. Yeah.
So it's about that person problem again. So we really need subtyping if we want to solve the expression problem. I mean, we have those 2 worlds. that approach with pure subtype systems that could solve precisely that thing?
So the expression problem is, well, so expression problem exists in OO languages as well, of course. And so, do you all know what the expression problem is? No. So in an OO language, it's easy to make what is it? So in Haskell, it's easy to make new functions, to write new functions over existing types, right? In the OO world, it's easy to make new types that work with existing functions, right? But what would be nice would be to, so if I've got a function that that works over, I know, syntax trees with 3 constructors, and I want to add a constructor, then in Haskell I have to go to all the functions that work over syntax trees, the one that counts the free variables, the ones that flips them over, the ones that takes their size, and I have to add a clause to each of them. So I have to go to this function, this function, this function, this function, and change it, right? So that's a bit tiresome, but if I want to add in an OO language, if I have a class for each kind of syntax tree, and then I want to add a new method to the class, say to collect its size, then I have to alter this class, that class, that class, and that class, right? And so the expression problem is how to solve that tension, right? And much has been written about this, right? And indeed people have described quite good solutions both in the OO world and actually in the Haskell world without using subtyping, curiously. I couldn't reproduce it for you today. I don't know. I suspect it's going to be because OO languages like Scala that have both generics and subtyping, that's probably the richest context. You're going to be most likely to get a good solution there. But at a price. At a price. Language design is all about this balance of intellectual complexity and compiler complexity and programmer complexity against the expressiveness and naturalness of the programs you get. It's not an exact science. Well, so my highly biased opinion is that I'm inclined to push hard on parametric polymorphism and give up altogether on subtyping. And I think we'll see, in the rest of these lectures, we'll see a number of sort of developments of the basic parametric polymorphism system that I think, some at least would be hard to integrate with if you were to try to think about subtyping as well. We shall see. Yeah, do you have a question?
Yeah. What is your take on structural subtyping, like the one you find in OCaml for polymorphic variables?
So do you mean when you like record subtyping? Yes. So this field is this record has got X and Y, and this other record has got X and Y and Z.
Yes.
Right.
Same for sense, yeah.
Right. So well, it's the same with all subtyping thing, right? It's like how would you not want that? And yet you walk into that swamp and it's expensive. I keep saying this. I'm sorry. I feel as if I'm like a broken record here. It's very difficult to do, combining with all the other good things you want. So again, for the same reason, we have no such record subtype. I mean, sometimes you can get things that are somewhat similar using parametric polymorphism. So for you know about row polymorphism. So if you have to take a record that says for all rows row, take records which have X of type int and Y of type bool extending row to a record that let's say I'm going to add let's say I'm going to delete a field from it, Y of type bool row. So this takes a record that has an X and a Y field and perhaps some more, and returns one that has only a Y field, not an X field, and perhaps some more. And so it's deleted the field, maybe it's modified the Y field, right? And perhaps it's taken the X field to modify the Y field. Well, so this looks more like parametric polymorphism than subtyping, though of course you could then call it on a record which has type X equals 3, Y equals 7, and foo equals 9. And you could also, so that looks a bit like, so sometimes, that's why the two kind of overlap again. See the way in which, very tantalizing. So people have played a lot with this kind of thing in Haskell. You tend to need to have some kind of constraint on row such that it doesn't have X and Y fields. So in T-Rex, it's written like this: row lacks X and Y. Meaning that this guy better not have an X and a Y field. And it turns out in T-Rex that this evidence here that's passed, instead of a type class V table, you pass the offsets of X and Y in the thing. It's quite nice. So, yes?
So you made this point about implicitness being a theme through Haskell.
Yes.
And indeed ML and many other parametrically typed languages, yeah.
But at least when it comes to memberships and type classes, that's explicit. Like, I have to say that this particular type is a member of this type class and then provide the listings. Is there some way type class membership could be made implicit?
Oh, well, wait, it's worth distinguishing two things here. That when you write the member function, do you remember I wrote that function right back at the beginning? And when we wrote it, we didn't have to write a type signature for it. We have to give an instance for the, we did have to make, we're using member in two different ways. When I write back at the beginning here, I wrote in this slide a type signature for member, but I didn't need to. I could have deleted the top line of this slide and it would have been inferred, right? So you can write functions which are kind of, whose types are inferred in a very ML-like way. The bit that you do have to do explicitly is this part, which is here, to make num an instance of, make int an instance of num. That we can't infer, because how would you, I suppose you could go around and say, well, look, I've got something called PLUS. I think that probably has something to do with this symbol plus, and it kind of has the right, I don't think you could do that. No.
Well, but we could have, like, we could have defined a method called syntactically the same as plus, right? Actually, that has plus with the same type.
Oh, well, I did. I wrote, I mean, if I hadn't, I could have written the code for plus int here. I didn't have to call another function. I mean, this is the definition of plus at int, right? So I had to call another function because I didn't want to write down what the code for adding ints looked like. But if it was list, say, well, oh no, let's say in the next example here, in the instance declaration, I really wrote down the code for equality in the instance declaration. I didn't call something else. Somewhere, I have to write the code that implements equality on lists. There's no two ways about it. I can't infer that code, and I just write it down as part of the instance declaration and say it is the equality function. I feel as though I'm missing your point slightly, but maybe we can talk afterwards. Yeah.
So, anything that can be done in Haskell type classes can also be accomplished by the ML module system?
Oh, sure. Yes. In fact, Bob Harper would say that type classes are simply a mode of use of the ML module system. A sort of, for, that is, a barely worth mentioning special case. Bob and I have a warm and loving relationship, as Dan will testify, but then everything is a mode of use of ML modules to Bob. I mean, it's a sort of lambda x dot. But to be truthful, so I mean, ML modules are amazingly powerful and expressive beasts, right? And indeed, you can do all type class things in a similar way. It's a bit less. What's the word? Implicit. So with these dictionaries that I was describing, the business of if I need eq at list of int, then the compiler will go around and will apply deq lists to deq int and build me a dictionary. So I'd need to do that explicitly in ML. Now, Bob and Manuel Chakravarti wrote a paper in which they describe how to take the ML module system and augment it with a kind of auto-generation of these kind of dictionary generation stuff, a kind of weird hybrid of ML and Haskell that would use the power of ML modules plus a bit of this implicit generation of code, which type classes are very good at. And I think Carl implemented it, did he not? Right.
Yeah.
So he has a kind of prototype implementer. Carl Query, this is.
Yeah, if you look at the way that people do type classes in Agile and Hawk as well, it's basically just construction. So you can use record type to implement the type classes, but then you use research to come up with these.
Right, Coq can generate this stuff implicitly too, right? Yes.
Yeah, but it's using, behind the scenes, what it's doing is it's just a record type, and then you do research to find instances of the record.
And of course, type class, finding type class dictionaries is simply a weak proof search algorithm. That's all it is, and we're going to see a lot more of that. So yes, but it's weak but useful. In fact, that's the whole story of types for me. Type systems are a weak but
predictable and useful form of theorem prover. Yeah.
I was going to mention one of the really useful things about type classes that I really talk don't give you is Haskell will make sure that you have canonical resolution.
Yes, unless you give it some random flag. But so there is. So,
but more than just the resolution mechanism, it's the whole conceptual framework.
Right. So the default assumption is for a type class there should be one instance. That's your sort of baseline. You deviate from that only after careful thought. Yeah, and but that probably is true of the kind of implicit generation that Coq or Agda would do as well, isn't it?
Well, in Haskell that can work at link time, right?
It's more enforced when you compile a module. We look at whenever you're resolving an instance, if there's more than one way to do it, we'll complain. So in theory, it could be done at link time. We could look at the whole program at link time and say, is there any two instances anywhere that conflict? But in fact, we don't do that for type classes, just for type functions, as we shall see. Yeah.
So I have two probably unrelated questions. First one is that you said before that the culture of Haskell and related languages is that essentially everything is implicit. But when you move to dependent types, you can't have this anymore. Do you have any thoughts or opinions on that?
Yeah. So I see it as sort of two ends of the spectrum, right? There's the sort of the foundation of the amazing glory of the Hindley, Demas, Milner type system for ML that says we can actually make a principal type for any program without any type annotations whatsoever. Just incredible, right? That you could. It's a beautiful sweet spot, right? That's at one end of the spectrum. And the other end of the spectrum is sort of everything explicit and decorated. But what has happened is then we always move towards the middle, right? So in a Haskell, here's an example of how we move towards the middle. In Haskell, you can have the way the ML type system works is that if you have a recursive function, you can only use the recursive. You can only call the function recursively at the same type, as it were, monomorphic recursion. So Haskell lets you do polymorphic recursion, not generally, but exactly when you have a type signature for the function. So if you supply a type signature for the function, as I did for member here, so then you can call the function, even if it's recursive, you can call it at some different type. So what that means is that you can make the type system more explicit by adding type annotations, right? Then it becomes more of a continuum, right? So we're adding type annotations to both document the program and to guide the type inference algorithm. Meanwhile, at the other end of the spectrum, highly decorated language with lots of types are busy leaving them out and doing type inference to fill the gap. And there's still a fairly big gap in the middle. And I suppose, again, my prejudice is I'm happier working from this end, but, there are no perfectly right answers here. What was your other question?
So the other might be more of a comment that the type class resolution in Conf is not canonical. And it's not needed always. And this is sometimes used productively, for example, for reflective automation.
There's two in Conf, right? There's canonical structures and type class.
Right. I think canonical structures are required to be non-overlapping.
Right. And then type classes is just.
Right, but I think canonical structures can overlap up to delta unfolding.
Okay. Good. I think we're tired. Thank you very much.